I am Dr. Harjinder Singh, Assistant Professor in Chemistry at Multani Malmodi College, Patiala. In this video lecture, we will discuss effect of conjugation over UV visible spectroscopy, and we will also discuss terms chromophore and oxochromes. So let us begin with effect of conjugation on absorption maxima, or you can also say on lambda max in UV visible spectroscopy. So we will discuss over here how conjugation in molecule affect this lambda max value in UV visible spectroscopy or absorption maxima in UV visible spectroscopy. Now, conjugation in molecule or the presence of conjugation in molecule always results in a lower the energy requirement for electronic transition. That means if there is a presence of conjugation, that always result in a lowering of energy requirement for electronic transition. Now, since energy and wavelength, they are inversely proportional to each other, so in presence of conjugation, the absorption take place at longer wavelength. So there is a decrease in energy requirement, or the absorption take place at the longer wavelength. So in presence of conjugation, lambda max, it always shift towards the longer wavelength. It always shift towards the longer wavelength due to the presence of conjugation, as conjugation lowers the energy requirement for the particular electronic transition. So let us discuss why conjugation results in a lowering in energy required for the electronic transition. So to discuss that, first of all, let us see what is conjugation. Now, conjugation basically is a delocalization of electrons, and this conjugation can take place either when double bonds are present in at alternating position like this. So here these double bonds, they can be delocalized by overlapping of p atomic orbital or overlapping of these pi bonds, which can intermix into each other. So there is a delocalization of electrons. Or conjugation can also take place when there is a presence of lone pair of electrons on an atom adjacent to this double bond. So here in this case also, these lone pair of electrons, they can be delocalized. So this kind of delocalization which take place due to the pi bonds which are present over the alternating positions, or due to the presence of lone pair of electrons adjacent to double bond, it is called conjugation. And this always results in a lowering of energy requirement for electronic transition and shift lambda max towards the longer wavelength. So let us see how it does. So to further understand this, let us take the example. For example, say you have a ethylene molecule. Now ethylene molecule is a simplest molecule containing one double bond. So in ethylene molecule, there is a pi to pi star transition, and this pi to pi star transition in ethylene molecule, it take place at 175 nanometer. Now since there is only one double bond and there are two electrons, so in ethylene molecule there is a one pi bonding molecular orbital. So suppose this is your pi bonding molecular orbital, and there will be one corresponding pi star anti-bonding molecular orbital. Now here in ethylene molecule, there's a one double bond, so there are two electrons, and these both electrons, they will be present in this pi bonding molecular orbital. Now this orbital, this molecular orbital, which is occupied, now here both electrons are there, so this orbital is occupied. Now this orbital is also called HOMO. So what is HOMO? HOMO is a highest occupied molecular orbital. So it is highest occupied molecular orbital. Here is this pi, and this vacant orbital is also called LUMO. LUMO is lowest unoccupied molecular orbital, and transition take place from this HOMO to LUMO or pi to pi star with absorption of radiations and UV visible radiation. So here this transition take here in this case this transition take place by absorption of radiations in at 175 nanometer. So this was the simplest case in which there is a one double bond. However, in ethylene molecule there is a no conjugation. In this case there is no conjugation. Now let's take the other example of the conjugated system. Now suppose you have 1,3-butadiene. Now 1,3-butadiene is this one. It's the 4 carbons are there, 1 2 3 4, so it's a butadiene. The double bond is present in 1 and 3 position, so it's a 1,3-butadiene. Now if you have 1,3-butadiene, now you can see 1,3-butadiene can be taken as a combination of two ethylene molecule. One ethylene molecule is this one, other molecule is this one, that are joined together by a single bond. Now here these two double bonds, they are present in at alternative positions, so they can undergo conjugation like this. So here in this case it is a simplest conjugated system that is contain two ethylene molecule. Now in this conjugated system there is overlapping between these two pi bonds take place. That means these two pi bonds, they can interact with each other or they can intermix with each other. Now since there are two pi bonds and total 4 electrons are there, so there will be two molecular orbitals. So one will be pi 1 bonding molecular orbital, pi 2 bonding molecular orbital. Always remember, in conjugated system the number of bonding molecular orbitals, that is always equal to number of double bonds. So here in this case there are two double bonds, so there are two bonding molecular orbitals, and corresponding to that there is an anti-bonding molecular orbital. So it will be say pi 3 star and pi 4 star, and number of anti-bonding molecular orbitals are always same as that of this bonding molecular orbital. So these are your anti-bonding molecular orbitals. So in case of ethylene there were two there was only one molecular orbital and there was only one anti-bonding molecular orbital and transition take place, but here you have a two bonding molecular orbital and two anti-bonding molecular orbital. Now since there are 4 electrons are there, so since each molecular orbital can have maximum of 2 electrons, so here 4 electrons they goes into these two bonding molecular orbital, and these two are remain vacant. Now as I told you, the transition take place from highest occupied molecular orbital to lowest unoccupied molecular orbital. So here highest occupied molecular orbital is this pi 2, so this will become HOMO, and lowest unoccupied molecular orbital is pi 3 star, so this will become LUMO. Now you can easily see as the number of molecular orbitals are increased, the gap between HOMO and LUMO is decreased. So you can see this energy gap between HOMO and LUMO is less. This energy gap is less as compared to energy gap between ethylene molecule. So gap between HOMO and LUMO is decreased, and since energy gap is decreased, so wavelength will increase. So here in this case this lambda max is, or the transition take place at 217 nanometer. So we can say as the conjugation increased or the double bonds in conjugation are increased, the gap between HOMO and LUMO is decreased and lambda max or the absorption maxima shift towards the longer wavelength. Similarly, for example, if you have beta carotene, Now, beta carotene is a pigment which is present in carrots, and here in this case there are 11 double bonds. In this beta carotene there are 11 double bonds which are present in conjugation, which are in conjugation. Now, since there are 11 double bonds which are in conjugation, so in this case gap between HOMO and LUMO is very less. And here in this case, so lambda max is very longer. And in this case, the absorption take place at a very long wavelength, or 455 nanometer, which is in visible region. So here in this case, this absorption take place at 455 nanometer in visible region. That is also responsible for the color of the carrots due to this beta carotene. So here in nutshell, we can say conjugation always results in a lower of energy gap for the electronic transition. So lambda max or the absorption wavelength shift towards the longer wavelength. And how it take place? By with increase in conjugation, the gap between HOMO and LUMO is increased as the number of bonding and anti-bonding molecular orbitals are increased. So gap between HOMO and LUMO is decreased and lambda max shift towards the longer wavelength. Okay, now next term is chromophores. Now this is a very important term. Now chromophore can be defined as any functional group. Chromophore may be any functional group. Now the word chromophore means color giving. Chrom means color, phore means forming. So chromophore means color giving or color forming. Chromophore is any functional group or it's any structural feature which is responsible for absorption of UV visible radiations. So chromophore may be any functional group or it may be any structural feature which is present in molecule and it is responsible for the absorption of UV and visible radiations. This chromophore, you can say this chromophore is responsible for absorption of UV and visible radiations. For example, if you take ethylene molecule. Now this is simple ethylene molecule. Now in ethylene molecule there is a absorption of radiations at 175 nanometer. And this absorption of radiations at 175 nanometer take place due to the pi to pi star transitions. And these pi to pi star transitions occurs because of the presence of this double bond. So here in this ethylene molecule, this double bond is responsible for absorption of UV visible radiations in this range. So this double bond in this case is a chromophore. Similarly, if you have a alkyne, so again in case of alkyne, the absorption take place at 180 nanometer. So here in this case lambda max is 180 nanometer. Now here in this case transitions take place due to pi to pi star transition, and here in this case this triple bond is act as a chromophore. We do not take this single bond as a chromophore because it is present in all organic compounds and it absorbs UV visible radiations of very short wavelength as we have discussed in first lecture. So the single bond is not a chromophore. So here double bond, here it is triple bond. Okay, similarly, suppose you have this molecule. Suppose you have this molecule CH3, CH2, and suppose I put hydrogen over here. Suppose you have this molecule. Now here in this molecule, this carbonyl group, it can show N to pi star transition and it can show pi to pi star transition. So UV visible radiations are absorbed because of the presence of this carbonyl group. So here this carbonyl group is a chromophore. Similarly, if you have a nitriles, so again here you have a N to pi star and pi to pi star transitions, N to pi star and pi to pi star transitions are there. So again it acts as a chromophore. So we can say the chromophore is any functional group or the characteristic feature in a molecule which is responsible for absorption of UV visible radiations, and these chromophores, they can be classified into two categories. The first type of chromophores are those in which there are only pi to pi star transitions. So the first type of chromophores are those in which there are only pi to pi star transitions, and the examples we have already discussed, like carbon carbon double bond, carbon carbon triple bond. So these are the chromophores, double bond and triple bonds, in which there is only pi to pi star transitions. And second type of chromophores are those chromophores in which there is a both pi to pi star and n to pi star transitions can take place. And the examples we have already seen, like C double bond O. Here in this case both type of transitions take place. N double bond N. So here also you can N to pi star and pi to pi star transitions can take place. N double bond O nitro group. So nitro group is this one. So here also these both transition can take place. So these are the N to pi star and pi to pi star transition. So these two type of chromophores are there. So in organic chemistry, we will deal with these two kind of chromophores. So we are interested in only these two transitions, pi to pi star and N to pi star transitions. The next term is auxochrome. So again, it's a very important term, auxochrome. Now what is auxochrome? Now again, auxochrome is any group. Auxochrome is any group which itself does not act as a chromophore. That means it itself does not act as a chromophore. This means it doesn't have N to pi star or pi to pi star transition, because chromophores are those that are having N to pi star and pi to pi star transitions. So it is a group which itself does not act as a chromophore, but when it attached with chromophore, it shifts absorption maximum towards longer wavelength with increase in intensity of absorption. So when it attached with chromophore, lambda max shift towards the longer wavelength. At the same time, intensity of absorption or epsilon max is also increased. So these kind of groups are called auxochromes. Now let us discuss with some examples. Now before going to examples, let us see how these auxochromes they work. Now previously, now here in this case, they shift wavelength towards longer wavelength. Now previously we have discussed effect of conjugation on lambda max, and we have seen whenever there is a conjugation, it always shift lambda max towards the longer wavelength. So how these auxochrome works? These auxochromes, they increase conjugation. So when they attached with chromophores, what they do? They simply increase conjugation. And when they increase conjugation, the lambda max automatically shift towards the longer wavelength. So these auxochromes, they are mostly they are groups that are having lone pair of electrons, like NH2, OH. So they have lone pair of electrons and they generally increase the conjugation. Or you can have OR, NHR. So these are the groups that are having lone pair of electrons, and due to the presence of these lone pair of electrons, when they attached with the chromophore molecule, they increase its conjugation and shift lambda max towards the longer wavelength. So let us see the example. For example, if you have benzene molecule. Now in benzene, the lambda max due to pi star transitions is 255 nanometer with absorption maxima of 203. So here epsilon max is 203. Now So here these double bonds, they act as a chromophore because the transitions are pi to pi star transitions. Now when oxochrome is attached, for example, suppose we have aniline. Now what happens, due to the presence of these lone pair of electrons, they undergo conjugation like this, and due to this conjugation the energy gap between the HOMO and LUMO is decreased, and here in this case this lambda max goes to 280 nanometer. So there's an increase in the lambda max, and this epsilon max, it also increased to 1430 value. So the attachment of this group NH2, now NH2 does not absorb the radiations itself because it consists of only sigma bonds. So attachment of this NH2 over this benzene ring shift absorption maxima towards the longer wavelength. So this group will be called oxochrome. Similarly, OH or any other group, this group which is attached will be called oxochrome. Let us take the another example. Suppose you have azobenzene. Okay, now this is azobenzene. Now here lambda max in azobenzene is 320 nanometer due to the pi to pi star transition, and this epsilon max is 21,000. And the other example is methoxy para ethoxy azobenzene. So this is simple azobenzene. Okay, this is simple azobenzene, this one, and the another one is para ethoxy azobenzene. That means at para position you have ethoxy group. So this is para ethoxy benzene. Now since there are double bond, there's a lone pair of electrons in conjugation with these double bonds, so there is a conjugation, and this conjugation increase lambda max value to 385 nanometer and absorption maxima to 42,000. And absorption maxima to 42,000. So here we can say this ethoxy group, it acts as a oxochrome. So this ethoxy group can be considered as a oxochrome. I'm facing some technical issues. So in this video lecture we have discussed the effect of conjugation over UV visible spectroscopy, and we have seen due to the conjugation the lambda max value or the absorption maxima always shift towards the longer wavelength due to the decrease in energy gap between HOMO and LUMO. Then we have discussed the term chromophore and oxochrome. Chromophore is any functional group or any characteristic feature which is responsible for the absorption of UV visible radiations, and it absorbs UV visible radiations by n to pi star or pi to pi star transitions or combination of these both. While in case of oxochrome is any group which when attached to the chromophore, it shifts its lambda max value towards the longer wavelength, and that happens by increasing conjugation. Thank you.